Okay, let us start with a new chapter. We're going to talk about moments of inertia. It is very similar to the way we used to compute center of gravity, except for this part right here is also used to better understand the stress distributions, the force distributions in a body. So let us begin with some introduction. So we know by now that we can find the resultant forces by summing um, or resulting areas, volumes, and in this case, inertia, by summing or integrating over the areas of interest. If we have regular geometries like rectangulars, squares, triangles, circles, and we have a geometry that is composed of a summation of those elements, I don't know, something like this. We have two rectangular shapes and a square, then we can add the areas of each element or each body. If we have non-regular shapes like parabola and etc., right on complicated geometries, we use the integration method of y squared dA. We'll see that in a minute. Now that is important because the moment of the resultant about an axis, by now we know that was determined by computing the first moment of areas of or volumes about the axis. Okay, so we're gonna see that there's a method that is gonna get us the parallel or to compute the momentum with respect to an arbitrary axis. So if this is axis x, there's a method to let us compute the momentum around x prime. And that is important because when we have a geometry that is not symmetrical, we might want to balance every force around a different axis. So we'll see how to do that in a minute too. Okay, so we want to understand how to get the magnitude of the resultant depending on the first moment of the force distribution with respect to an axis. So all this that we're going to learn is really to know how to compute resultant forces with respect to an axis. Okay, and the point of application of our resultant depends on the second moment of the distribution with respect to the axis. So that's why the second moment is so important. This chapter chapter 9 in this book, is focused on teaching us how to compute the second moment, or also called moment of inertia, for areas. You can also do it for volumes, but we're going to start in 2D. All right, so this is basically the whole concept. Once you get this concept, we're ready to go. So consider distributed forces delta F bar. This means a vector, and whose magnitudes are proportional to the elements of the area. Okay, so maybe later, I don't know if this class will get us to get that far, but for sure later, you will understand that pressure is a force divided by an area. And let's assume that we have a wall and there's water touching or against the wall. So, and in this case, for instance, what all we're doing is we're saying that, let's say that distribution of all the forces, delta F, is equal to the pressure that we get here, which we know by now that is rho GH, and this term, the density times the gravity, is also called gamma. And H obviously is Y, right? Because here we have the height in the Y direction. And this is going to be proportional for this example as the delta area. Meaning that if you get a larger area to study, the force on that larger area is going to be larger because it's just scaled by a pressure P. Okay. All right. We know by now that that pressure P is linear. If you do a side view of this guy right here, you remember that wherever the line water or the line of the liquid begins, the pressure builds linearly. So that's the distributed force. So when we start doing the second moment of inertia, we can compute this with y squared delta area. All these are typos. I don't know why they got this typo here. But focus on this part. All we need to do is to get the y squared, which is not necessarily the easiest thing sometimes, but we can definitely find it, and we'll go through some examples. So remember that we used the integral of y dA for centroids, central point of gravity, but y squared dA is going to be for the area of moment of inertia, or the second moment of area. So this is pretty much the concept. This is integration right here. It's a typo. If you want to find the second moment of inertia with respect to an axis x and y, it's pretty simple. It's with respect to the axis x, is integration of your function y, which is a function of x, squared dA. So for instance, if your function y of x was a wave, a perfect wave, say sine of x, the second moment of inertia with respect to the given axis for that wave, let's say it's like this, and axis x and axis y. The moment of inertia with respect to x is sine of x, everything squared, dA, not just x squared, everything squared. All right, the same thing for the axis of inertia with respect to y. You do an integral of x squared dA. All right, so on a rectangular area, the inertia with respect to x is equal to 1/3 bh cubic. So there's going to be a table with all the inertias for the given areas that we usually get to apply. And those areas will be the common, uniform, or yeah, the areas that objects that are regular objects, such as square, triangle, rectangular, etc. So we already found one. The inertia with respect to x for a rectangular shape is 1/3 of base times height cubic. The next important concept is the polar moment of inertia, and that is mostly used for rods or circular objects. So if you have a rod, something that is used like on an axis for a car, for a truck, for a hydraulic actuator, this, when you use it on an axis for a transmission, you get a torsion. To compute this torsion, you'll see later, maybe we even get to see it in this chapter, depending on how far we can get. To compute this torsion, you're going to need something called the polar moment of inertia, because that is going to give you information about the area, about the geometry. So to compute the polar moment of inertia, you use integral, or the radius, the function with respect to polar coordinates, dA. Remember that the function with respect to polar coordinates is radius and an angle. You can always get your coordinates in polar coordinates with sines and cosines. So in this case, all you need to do is to remember that the polar coordinate is the inertia in x plus the inertia in y. All right. Now, the other important concept is the radius of gyration, and that is usually given by the letter k, and that is also related to rotation. So, and as you remember, all this has to do with moments. So K is computed as the square root, well, gyration with respect to x is the square root of Ix divided by area. Ix is the second moment of inertia with respect to x. And remember that this second moment of inertia with respect to x is the integral of your y squared dA if it's a non-regular geometry. If it's a regular geometry, we're going to learn that there are already functions and formulas for us to use. And the inertia with respect to y is the same thing, is the square root of second moment of inertia at y with respect to a. So this is a problem right here that is not a regular geometry because it's not a rectangular. It's not a triangular. It's not a triangle with rectangular unit angles. It's a specific type of triangle that is not uniform. So we know by now that we find the inertia in x with the y squared dA. The trick here is to form the function for y. If you want to use this, if you want to go into details with this example, you should. But I feel that this type of example is more for a calculus class than for statics. So I'm just going to mention that the important thing is to get your function and your differential. All right, so your function is y squared and your differential is going to have a y. And you're going to transfer your dA to your dy. That is usually what is going to end up happening. Your dA is going to transfer into a dy times a factor. All right, integrating this guy, you're going to get the inertia of that object, which is type of triangle that is not a rectangular triangle. That inertia for that object is going to be base times height cubic divided by 12. So every time that you have a triangle like this, any triangle is going to be 1/12 of base times height cubic. Let's go over a second example. Also, again, this is good for a calculus class, but here is just to start getting an intuition of how these formulas get derived. So we have a circular object, well, a circle, and is using an annular difference area. So we have a distance u, a du, and the radius is to the external diameter. To find the polar moment of inertia, we also have to take into account the radius, so the internal radius is u. So it's u dA, differential of area. All right, so we have to transfer the differential of area into terms of the u. And if you remember calculus, we have something called perimeter, which is 2 pi r, and the u is going to be, as we said before, the trick is to get the differential of area in terms of your differential of your coordinate. So in this case, that gets the differential polar gets transferred into a integral of your u squared. So from 0 to r, because that's the maximum radius, you're gonna get u squared dA. Here you integrate this, and it gives you the polar inertia and the polar moment of inertia is pi. I don't know why they have p. Pi over 2 divided by sorry, pi divided by 2 times r to the fourth power, and r is the external radius. So anytime you have a circle like this, your polar moment of inertia is going to be pi over 2 times the radius of the circle to the fourth power. So you don't have to derive every single time. Now you just have to build a table that I'm going to give you. Take that table and you start using it for the problems.